Alright, so this video is on parent functions and transformations, and you've heard of both of these things before in previous math classes. So I'm just going to remind you of what they are. So for example, the parent function for an absolute value graph would be y equals the absolute value of x. The parent function for a linear graph would be y equals x. For a cubic graph would be y equals x cubed. For a square root graph would be y equals the square root of x. So the parent function is just the function without any transformations happening to it. It's like the most simple example of the function. So the transformed function for an absolute value would be a times the absolute value of x minus h plus k. And each of these different variables, well, not variables, they're constants. Each of these different constants means something for the problem. So the a value could refer to three different things. If it's a negative, it means that the graph was reflected over the x-axis. If the absolute value of a is less than 1, it means that the graph was vertically compressed. If the absolute value of a is greater than 1, it means that the graph was vertically stretched. So when I say a negative here, I mean any negative number. It doesn't matter if it's less than 1 or greater than 1. Size-wise, it doesn't matter if it's a decimal or a fraction or if it's a number bigger. As long as it's negative, it means it's been reflected. And then likewise, these ones, the sign of them don't matter. That's why they're in an absolute value sign. So it is a coincidence that I happen to do an absolute value graph. But what these really are referring to is that the size of the number is smaller than 1. So 0.5 or negative 1/2. Those are the same, or 1/7 or negative 5/6 or 0.27 or something like that. Those would all be compressions because the size is smaller than 1. So it's taking the normal height of the graph and it's compressing it down, it's squishing it. Anytime the size of the number is bigger than 1, it's going to be a stretch. So it doesn't matter if it's negative, it still would make it a stretch. So that's the number in the front. The number inside is going to tell you if the graph has been shifted to the left or to the right. If it's a positive number, it went to the left. If it's a negative number, it went to the right. So I always think of this as it's the opposite of what you would think. And then the number on the end tells you if the graph has shifted up or down, positive for up, negative for down. All right, so what we're going to do is we're going to look at an example of a transformed graph, and we're going to figure out what all the different points would be once they've been transformed, and then we can sketch the graph. So we have y equals negative absolute value of x plus 3 plus 2. So before I get started, I'm going to want to know what the different values are for the parent function. So I'm going to go ahead and make a table of values. So typically we'll use -2, -1, 0, 1, and 2. And we'll do that for most of the functions except for a few of them. And this is a process that we're going to do right now beginning in the semester, but we're also going to do it later on in the semester each time we look at analyzing different functions that we maybe are rusty on, or different functions that we're learning about for the first time. So this is a process that we're going to repeatedly do. So make sure you're doing your best to try to understand it. So the x value of -2, if I put that in absolute value symbol, that's going to be a positive 2. -1 would be positive 1, 0 would be 0, 1 would be 1, and 2 would be 2. Okay, so I'm going to start with those points. I'm just going to write them down. And then I'm going to apply each of those transformations to them. So, and I'm going to go ahead and do the transformations in the equation from left to right. So the first transformation that I see is that the graph has been reflected over the x-axis. So that means that if the graph originally went up, then I'm going to flip it and it's going to go down. So any y values that were positive are going to become negative. Any part of the graph that was down is going to flip up. So any y values that were negative are going to become positive. So that means that we're going to take the y coordinates and we're going to multiply them by -1. All right, so what I did is I did the transformation of reflect over x, and to do that, I multiplied y by -1. All right, so that transformation is done. The next transformation I have is that I'm shifting the graph to the left 3. So I'm going to take each of my x coordinates and I'm going to shift them left 3 by subtracting 3 from each x coordinate. So if you think through the transformation, you can actually kind of reason your way through if it should be done to the x coordinate or the y coordinate. So when you reflect something, you're going up and down. That would happen to a y value. If you're shifting something to the left, that should happen to an x value. So here our transformation was left 3, and so we subtracted 3 from x. All right, that's a weird looking parenthesis. Go ahead and put the whole thing. There we go. All right, and then our last transformation is that our graph needs to shift up 2, and so I'm going to do that to the y coordinate. And what I typically do is I do 2 columns usually, well 3 because I have my starting points. The first column I do anything to the points that needs to multiply by the number, and then the second column is where I typically add or subtract, and I just do that to keep track of my order of operations, that you have to multiply numbers first and then you can add or subtract them. And once you're done with this, these points right here are the points that you're actually going to graph. So before I forget, I'm going to say this was up to, and we added 2 to y. Okay, that looks like it says toy, but it says 2y. Okay, so I'm going to go ahead and graph this. So I've got -5, 0, -4, 1, -3, 2, -2, 1, -1, 0. And so if I look at this, then I have an absolute value graph. It's upside down. It's been moved left 3 and up 2. So I can see that that's definitely my function. One more thing that I would like you to be able to do from these equations and from the transformations is I'd like for you to be able to see where the vertex is. So if you notice, a normal absolute value graph would have a vertex at 0, 0, and this one moved to the left 3 and up 2. So it did the transformations left 3 up 2, and that means that for us to find the vertex, we don't actually have to graph the equation. We can look at the equation right here, and the opposite of this number and this number give us our vertex. So the vertex here is -3, +2. So the vertex is always relatively easy to find. Okay. The next equation that we're going to work with, or the next parent function we're going to work with, is a quadratic. So that parent function is y equals x squared, and the transformed function would be a times x minus h squared plus k. So you can see there's a lot of similarities between the transformed functions. So here, the transformations actually mean the exact same thing, so we don't have to write them again. We have reflect over x, vertical stretch, vertical compression, left, right, up, down. All right, so the difference here is that instead of having an absolute value graph, we have an x squared graph, so we need to start with different values for y. So we can still plug in -2, -1, 0, 1, and 2, but this time when I plug those numbers in, something different is going to happen. So if I plug in -2, I get 4. If I plug in -1, I get 1. If I plug in 0, I get 0. If I plug in 1, I get 1. And if I plug in 2, I get 4. So when I see an equation that looks like this and it has the little exponent of 2, that just tells me that I'm going to do the transformations the same way, but I need to start with this information instead of starting with that information because I am transforming a different parent graph. So I'm going to go ahead and write an example problem to work with. We're going to do y equals 3 times x minus 1 squared minus 4. And so I'm going to write these points down. All right, so the first transformation that I see is to vertically stretch by 3. And since it's a vertical stretch, we're taking how tall the graph is, we're making it 3 times as tall. And so I'm going to take the y-coordinate, because that's an up and down change. I'm going to take the y-coordinate and multiply it by 3. All right, so I vertically stretch by 3. And what I did there is I multiplied y by 3. The next transformation that I see is I'm going to move to the right 1. So all my x values need to have 1 added to them. So we did right 1, so I added 1 to x. And then we're going to shift down 4, so I'm going to subtract 4 from all the y coordinates. And I'm not going to graph this one. But if I did, I would be able to see that parabola. However, without even graphing it, I can go ahead and find the vertex. So I'm going to circle these two numbers. The vertex for this parabola would be 1, negative 4.